Hi, this is Mr. Adams from Midwood High School, and this is a video on the common ion effect. This topic will be in our test in a few days, so here's a bit of review. The common ion effect is very, very closely related to Le Chatelier's principle. And we talked about Le Chatelier's principle in class, and it's also in another video that we did. But as a reminder, Le Chatelier's principle simply states that if you have a system at equilibrium and you cause stress to it by changing the concentration, pressure, or temperature, okay, the reaction at equilibrium will shift to a direction, either right or left, to relieve that stress and reestablish equilibrium. In the common ion effect, you're normally adding some ion which is in common with the species in the reaction. And normally what happens is that you get a decrease in solubility. Now, if that sounds kind of weird, don't worry about it. We'll do an example in a second. The common ion effect has some practical implications in real life. I'm sure you've seen at some time this scaly product that happens on taps and on boilers and stuff like that. That's common ion effect is used to help get rid of that. It's also used. This was talked about in your homework reading in the textbooks in order to help with when they're taking pictures of your insides when they use barium sulfate to control the amount of barium ions in your body, and it's also used in the production of soap. Okay, to push your reaction in a specific direction. All right. Now, when you have a question, right, and you're doing an example with a common ion effect, you simply look at the equation and the species involved. For example, you have a reaction right here. You notice on the reactant side, we have a solid ionic compound, and on the product side, we have ions, right? Because you see the charges, they're ions, okay? And they're in the aqueous phase. We take all those things in consideration. The next step, you determine how substance added dissociates. So, for example, in this example over here, we'll be adding sodium chromate. All right, and we're going to figure out in a second how does it dissociate. Now, after that, you find ion which is in common, and then you add it to that side. So you find ions which are in common, and you add to that side, and then you figure out the shift. So let's do the example. We have sodium chromate over here. So sodium chromate is Na subscript 2 CrO4. Okay, and it's an ionic compound because this part right here is metal and this part is non-metal, right? And if you come to, as before, if you come to a compound and it looks kind of weird, normally if it has 3 or more substances, elements in it together, and it's ionic, some part of it is going to be on table E, polyatomic ion. You look there if you're not quite sure, but this is sodium chromate, if metal and non-metal parts. Now, what's going to happen when this guy dissociates or breaks apart? You will get 2 NAs, which have a +1 charge. Remember, you have your reference tables, and you'll get a chromate, polyatomic ion. Okay? Now, be careful with your polyatomic ions. Please don't break them into pieces. Please don't say CRs and O's. And no. It's just CrO4 2- acting as one unit, carrying a 2- charge. All right. So this is what you'll get, okay, when sodium chromate, this guy right here, dissociates. Okay. Now you look at the equation, our original equation, we see that we don't have any Na anywhere in here, right? So NAs we are going to ignore for now because there's nothing in common there. When we look on the equation again, we see that we have a CrO4 2- ion in common with this CrO4 2- from the substance that we're adding. So what we do next, guys, we simply add more CrO4 to this direction right here, to this this side right here, because we have original CrO4 over here, and we're adding more chromate ion over here. So we add to this side. And before, when we did the Chatelier's principle, if you're adding a particular substance, you will get a shift away from that side. So in this particular equation, this reaction, the reaction will shift to the left. It will shift to the formation of reactants. Okay, so we're adding more CrO4 right here, and it's going to shift to make more of this guy right here, this solid lead chromate. your solubility therefore will decrease because you're making more solid lead chromate. And what's happening, the chromate is reacting more with the lead. Okay, from the collision theory that we talked about before, the lead ions will get used up with the chromate to make more solid lead chromates. Okay, what happens next is you're losing lead ions. Your lead ion concentration will go down. You're making more solid, so your solubility decreases. And once again, there's practical implications. Let's say you have lead ions somewhere contaminating, I don't know, drinking water, for example. You can use a common ion effect to reduce those ions in solution, making them, less harmful to the environment and to our bodies. I hope this video was a help. As always, hard work plus sacrifice equals success is a common ion effect. It's a nice, simple extension of the Chatelier's principle. And I'll see you guys in class. Take care.